of freedom to make your basis functions vanish at most of the quadrature points, then most of your operations involve zeros, and then you get a complexity which is optimal. But you don't get anything back. You know, I was saying I'm a mean guy. If I'm going to have to work 6 times harder or use 6 times as many functions, I want to get at least 6 times as much benefit. You don't get any benefit at all. It's no faster converging. The constant isn't significantly smaller. The only thing is that you can compute these functions a bit faster. So that's, in a sense, that's it. If you're a pure mathematician, that's the problem solved, go on to a new one. But if I've got to pay for the computer time, that is not an acceptable solution. All right, here's my claim. The Bernstein Bezier basis achieves optimal complexity without tinkering with the basis. So that, I mean, this is the real meat. You know, remember I'm starting off. What advantages, if any, does integrating techniques from Bernstein Bezier graphics visualization bring to finite elements? Here's a concrete result. You get optimal complexity for evaluation of the mass matrix. Any number of dimensions. Okay, let's see how it's done. So there's the mass matrix, and here's a property of Bernstein polynomial. Product of 2 Bernstein polynomials of Bernstein polynomial with some messy factor. What that means is that when I plug that identity into there, I get an alternative expression for the mass matrix. It's just this moment thing. So these are now moments. What I've done is turn the computation of that tensor into the computation of a moment. This is the moment of the data C against the Bernstein polynomial of degree 2n of index alpha plus beta. So remember, I've got an efficient algorithm for calculating moments. So now I've